Welcome to the topic on purity of substances. In this topic, we are going to learn in detail about importance of the purity of substances. We would learn about the characteristics of pure substances so that we can identify if a substance is pure. Determination of melting point of a substance, which is an important aspect in determining the purity of a substance. Then we will look at how to determine the boiling point of a substance. We will also learn how to identify the purity of a substance by using paper chromatography. Melting point diagrams of binary alloys that could let us understand how alloying of metals affect the melting points of the mixture. Lastly, we would take a look at what are the physical characteristics that a substance can possess. We need to identify the purity of substances for various reasons as given below. Pure substances would give us the freedom to customize a mixture according to the ratio of the substances that we want to mix. Let us say that we would like to create a mixture of copper and gold in the ratio of 9:91, then we could take 9 grams of pure copper metal and 91 grams of pure gold ingots, and then melt and mix them together. If the copper or gold used is not in its pure form, then we would not be able to create a perfect mixture according to the ratio that we want. Hence, pure substances give us the freedom to create any mixture according to our requirement of mixing. Pure substances can help us to create various alloys according to the engineering property that may be necessary. Various engineering applications require various combination of physical properties, such as lightweight, corrosion resistance, strength, malleability, and so forth. For the needed combination of properties, various quantities of pure metals are added together to create the metal needed for that specific application. Purity of precious metals, such as gold, silver, or platinum, would determine the market value of the metal. The price of a precious metal would of course be lower if it is in impure form or if it is mixed with other metals. For instance, ornamental gold used to make jewelry costs less than the pure mint of the gold coins or biscuits that can be purchased from banks or gold mints. Purity also plays an important role in the food and pharmaceutical applications. This is because any consumption by a living things could adversely affect the health if there are other substances found in them even in trace amounts. For instance, iron supplement tablets given to patients who are anemic cannot contain impure iron with traces of lead. Hence, pharmaceutical-grade iron with high purity is used during the manufacturing process. Purity is the key to manufacturing silicon-based semiconductors, as the amount of impurities can change its electrical characteristics drastically. Addition of impurities in a carefully controlled manner are employed during manufacturing using silicon substrate by a process known as doping. As we can see, purity of a substance plays an important role in our everyday lives. What are the characteristics of pure substances? How do we identify them? Well, it is important to know that a pure substance would certainly look pure throughout. If someone told you that a milk is pure, and when you look at it, it contains some black particles floating on it, would you consider it as pure milk? Throughout the substances, the color should remain exactly the same, no matter which part of the substance you take to compare. If we measure the density of the substance from various parts of the substance, it should give the same density at the same temperature. Density is the amount of matter packed in a unit volume of the substance, and a pure substance should have the same type of packing of its particles throughout the substance at the given temperature. A pure substance would melt or freeze at one single temperature and never over a range of temperatures. This is one of the easiest ways to identify if a substance is pure. Pure water should freeze exactly at 0 degrees Celsius, and pure ice should melt exactly at 0 degrees Celsius. If ice is found at any temperature above 0 degrees, or if liquid water is found at any temperatures below 0 degrees, we can be certain that the water is not pure. Likewise, a pure substance would also vaporize or condense at one single temperature and not over a range of temperatures. This is another one of the ways to identify if a substance is pure. Pure water should become steam exactly at 100 degrees Celsius, and steam would condense to water exactly at 100 degrees Celsius. Boiling points can be used to determine the purity of liquids by measuring it. Another one of the ways to identify purity of substances is to use chromatography. Some inks or food colorings are made by mixing a few dyes together. If in a chromatogram a single spot appears, then it is pure. If there are multiple dots, then the substance is a mixture. A pure substance cannot be separated into different components using any of the physical separation methods such as filtration, evaporation, distillation, sublimation, etc. For example, if you filter a pure water using filter paper and you manage to see some residues on the filter paper, it is obvious that the water is not pure. Thus, by knowing the characteristics that define pure substances, it would be easier for us to identify them. Since we know that a pure substance has a fixed melting point, we need to understand how to measure the melting point of a substance. Let us look at the procedures. Firstly, take a clean test tube and place the solid whose melting point needs to be determined. Then, tie a thermometer using an elastic band or a rubber band with the bulb of the thermometer in line with the solid in the test tube. The placement of the bulb in line with the specimen is important so that it measures the temperature of the solid as accurately as possible. If the bulb is above or below, then it might measure the temperature at that point rather than the temperature of the solid. The next step would be to immerse the above arrangement in a boiling tube containing an oil bath. Of course, make sure that the boiling point of the oil or any other fluid that we use is higher than the melting point of the substance. Otherwise, the oil might vaporize even before the solid melts, and it would defeat its purpose. We should avoid direct heating of the specimen, as it would be difficult to measure the exact melting temperature. By placing the test tube and the thermometer in the oil bath, we are making sure that the temperature rise is gradual and uniform as the solid melts. It is a good idea to use a stirrer in the oil bath to ensure that heat is uniformly circulated and any convection in the oil does not cause uneven temperature in the oil bath. Now that the setup is ready, we can start to heat up the boiling tube over a gentle flame, making sure that the heating is gradual and slow so that any melting can be comfortably observed. You may need to remove the flame from time to time if you notice that the rise in the temperature shown by the thermometer is too rapid. Keep observing the specimen. When it starts to melt or turn into a liquid, take note of the temperature. Keep observing the specimen and the temperature throughout the process of melting. If it is a pure substance, the temperature at the start of melting and the completion of melting should remain unchanged throughout. We can conclude that the temperature at which the solid melts is the melting point of the solid. There are some important points worth remembering when determining the melting point of a solid using this method. As we mentioned earlier, the bulb of the thermometer should be in line with the specimen whose melting point is determined so that the temperature shown is indeed the melting point of the solid and not the surrounding temperature. The next point to take note is that the boiling point of the oil bath should be well above the melting point of the solid. If the oil boils off even before the solid melts, it defeats the purpose of heating over the oil bath. Heating too strongly could cause the melting point to be missed due to rapid rise in temperature. Therefore, gentle and intermittent heating ensures that the rise in the temperature is gradual and noticeable. If all the solid melts at a single fixed temperature, then it is a pure substance. If the temperature keeps rising when liquid has already started to appear in the tube, or if we can still see solids even at a higher temperature, then we know that it could not be a pure substance. The next point to remember is that the temperature range of thermometers should be able to measure the melting point of the specimen. We cannot use a thermometer that can measure up to 100 degrees Celsius to measure the melting point of a substance which melts at 150 degrees Celsius. This is quite obvious, though it must be still mentioned. Let us take a look at how to measure the boiling point of a liquid. Since a pure substance would have a fixed boiling point, we could determine its boiling point by using the following method. Place the liquid in a boiling tube, which has a nose for the vapor to escape, as shown in the diagram here. The vapor must be able to escape freely so that the pressure above the liquid remains at the atmospheric pressure. We could also attach a manometer to the boiling tube to check if the pressure of the vapor inside the boiling tube is at the atmospheric pressure. Then, place a stopper on the tube with a hole for mounting the thermometer as shown here in the setup. Next, insert a thermometer, making sure that its bulb is in line with the nose where the vapor escapes from the boiling tube. Do not immerse the bulb of the thermometer into the liquid. What we are trying to measure is the boiling point, which means the temperature at which vaporization of the liquid takes place. Therefore, we should measure the temperature of the vapor rather than the temperature of the liquid. Lastly, heat the boiling tube gently using a gentle flame so that the temperature rise can be noticeable. Keep observing the nose of the boiling tube to see the evolution of the vapor. Once the vapor starts to form, observe the temperature shown by the thermometer. If the liquid is a pure substance, the entire liquid should boil off at one single temperature. In other words, the entire liquid in the boiling tube should vaporize, leaving an empty tube, while the temperature remains at the same level, if the liquid was pure. The temperature at which the vaporization took place is the boiling point of the liquid. In order to understand the fixed melting and boiling points of the pure substances, we need to understand in terms of the energy supplied to the particles or the substance. Temperature of a substance indicates the kinetic energy of the particles. Energy supplied to the substance can be used to do either of two things. It can be used to increase the kinetic energy of the particles, in which case the temperature can increase. Or it can be used to break the bonds holding the particles together in the given state. In this case, the particles would continue to move with the same speed, and hence the temperature will not increase or decrease. Remember once again that increasing the kinetic energy increases the speed of the particles and hence the temperature of the substance. However, during the breaking of the bonds during a state change, the kinetic energy, the speed as well as the temperature remain constant since the energy is used to break the bonds without increasing the kinetic energy further. The change in temperature or the change in kinetic energy occurs when the substance is in the same state and the bonds are still holding the particles together in that state. The breaking or forming of the bonds happens when the substance changes from one state to another. When temperature of the substance is plotted against time of supplying the energy or against the amount of energy, the following heating curve can be obtained. As we can see, when the heat energy is supplied to the substance, the Ke as well as the temperature increases gradually due to the increase in the speed of the particles until the maximum speed in the solid state is reached. At this temperature, all the particles in the solid state vibrate with the maximum speed. The energy supplied to the substance beyond this point is used to break the bonds holding the particles in the solid state. With the breaking of the bonds, the substance enters into liquid state and the particles gain greater freedom of movement. As more bonds are broken, more liquid is formed. Throughout this process, the speed and hence the temperature of the particles remain constant. When the last bond in solid state is broken, the substance is ready to enter into liquid state. If we keep supplying energy beyond this point, the kinetic energy as well as the speed and the temperature of the particles of the substance increases once again. This is due to the greater freedom of movement in liquid state, where the particles are no longer bound tightly to each other, unlike in solid state. The temperature keeps rising once again, till the maximum speed of the particles in liquid state is reached. As the particles cannot move any faster, the energy will once again be used to break the bonds holding them in the liquid state. As more and more of the bonds in liquid state breaks, the substance turns into vapor or gaseous state, which gives it complete freedom of movement. When the last bond in liquid state is broken, all the particles have complete freedom of movement, and hence the kinetic energy can increase once again infinitely. The first part of the curve represent the substance in solid state. The second part represent the liquid state, and the uppermost part of the curve represent the substance in gaseous state. This is how a typical heating curve of a pure substance looks like. The temperature at which solid to liquid transition occurs is called the melting point of the substance. Similarly, the temperature at which liquid turns to gas is called the boiling point of the substance. At this point, melting hasn't started, and all the particles are in solid state. At the end of this line, all the particles have entered into liquid state as melting is complete. Here, we would have a mixture of solid as well as liquid particles. This point represents the starting of vaporization, and all the particles are still in the liquid state. Here, all the particles are in gaseous state since it marks the end of vaporization process. In between the two extreme ends of the horizontal line, we would have a mixture of liquids and gases. The name of the process of changing solid to liquid is called melting. The reverse process of changing liquid to solid is called freezing. Likewise, the process of changing liquid to gas is called vaporization, and the reverse process of changing gases to liquid called condensation. Just like the heating curve, this is how the cooling curve of a pure substance looks like. Of course, the temperature decreases as the substance cools down. Similar to the heating curve, during the cooling, the temperatures remain unchanged during a change of state. The temperature at which vapor condenses to form liquid is called the boiling point, and the temperature at which liquid solidifies or freezes to form the solid is called the melting point or the freezing point. Chromatography can be used as another way of checking for the purity of a substance. In this chromatogram, let us compare a couple of inks. What does the result show? It shows that the ink one is a pure dye since it contains only one dot. However, we can see that the ink 2 is a mixture of 3 different dyes, since we can see 3 distinct dots for the ink 2. Next, let us understand what alloys are and how their melting point is affected by the amount of the alloying elements. Binary alloys are a mixture of 2 metals that have been melted, mixed together, and then allowed to solidify. Melting point of the alloy can be plotted against the percentage composition of the alloying metal. In this example, let us take the binary alloy of lead and tin. The horizontal axis indicate the percentage of tin in the mixture. If the percentage of tin is 0%, then the remaining 100% is pure lead. If the percentage of tin in the mixture is 60%, then the remaining 40% would be lead and so forth. In a heating furnace, 100% of pure lead ingots are added, and it will melt once its melting point is reached. Lead melts at 327.5 degrees Celsius, and this can be plotted on the left axis where the percentage of tin is 0. Alloying metal of tin is added to the molten lead to increase the percentage of tin in the mixture. As we can see from the graph, the melting point of the alloy begins to decrease as the percentage of tin increases. Beyond 60% of tin in the mixture, the melting point of the mixture increases again. When the alloy does not contain any lead, which is when the percentage of tin reaches 100% of pure tin, the temperature of the melting point of pure tin is plotted. Pure tin has a melting temperature of 231.9 degrees Celsius. As we move from the left to the right of the graph, we can notice that as the percentage of tin in the mixture increases, it implies that the percentage of lead decreases accordingly. We can also see from the graph the melting point of alloy at any composition is lower than the melting point of pure lead. Lastly, let us look at the effects of impurities. Impurities can change the physical characteristics of the substances. In order to understand, we must know what the physical properties that substances possess and how they can be changed. Physical properties include the density of a substance. Addition of impurities changes the mass per unit volume of the substance, since different substance has different packing of the atoms as well as their relative masses. The color of the substance is another physical characteristic that can be changed by the addition of impurities to a substance. The melting as well as the boiling point of a substance is the next physical characteristics that can change due to the presence of impurities. As we have seen earlier, the pure substance melts or boils over a single fixed temperature, unlike a mixture which changes state over a range of temperature. Electrical resistance of a substance changes due to the impurities. For example, nickel-chromium alloy is used to create high-resistance wires used in electrical heating applications. Malleability is another physical characteristics in which a substance can be bent or hammered easily without breaking. Malleability of some metals are improved by alloying the base metals with other metals. Hardness is also a physical character which changes with adding impurities to a pure substance. During alloying process, atoms of different types of metals having differing atomic diameters are used to lock the atoms in position, thereby increasing the hardness of the alloys. Impurities does not refer to contamination. Contamination is unintentional. Adding impurities to improve the physical characteristics are intentionally carried out. Impurities simply refers to a mixture of substances instead of using just a pure substance, and therefore must not be confused with contaminations. That's the end of this lesson. Hope you have enjoyed learning this topic. Till we meet again, have a great day from all of us at Donison Dean Research Center, Singapore.